We have done rotational motion, so we've looked at the dynamics. We have done inertia. We have done center of mass, so we've looked at how hard it would be to rotate something about some certain axis, and its center of mass, so where it would naturally want to rotate, and then some of the dynamics. We've done center seeking forces. So now we're going to look at what forces are required to rotate something. And I wanted to define a few of these things for you. I've been doing the circular motion, and I've done the little vector showing your tangential velocity, and then this would be like, your center seeking acceleration. So we can think of, our tangential acceleration either being in the direction of our tangential velocity or like being opposed to the tangential velocity. But this would describe something speeding up or slowing down, right? Because if this is slowing down, wouldn't the rotation have to be slowing down too? Now, I want to separate that out, though, from the acceleration from center-seeking motion. So this would be something if I just like put a line in it in the middle and then spun this thing around it. I would be looking at some amount of force that's required to spin it. But it's not moving, it's not traveling across the ground when I do that. So my center seeking force is really not all that exciting, right? This thing here would be if I have something rotating and translating, and it's doing so in a circle. So this is a rotation about a fixed axis. And if I make this thing rotate in a circle on the ground instead of going straight on the ground, then I'd have some sort of center seeking force. Hopefully that gets that for you. Now, for the forces that make that rotation happen, we define that thing in terms of this letter tau, is what that's called. And that is defined as torque. Torque is this cross product between the radius, distance of rotation, to the force being applied. So in this example here, I have two forces that I'm applying. The radius is the distance from the axis of rotation, would be here. And so this distance here times this force here is part of what gives me the torque. This cross product just pops out the sine of that angle. So what we're looking for is the force piece, the force component that is perpendicular to the object, or maybe a better way to think about it would be perpendicular to the axis of rotation. So if I push this down, this block thing would rotate like that. I'm sorry, would rotate like that. There we go. Let me do a better picture. So I'd apply a force here, and it's rotating that away. So this force I'm applying is perpendicular to the axis of rotation. If you can kind of see that. That's what this is pulling out. So you're looking for the y component, essentially, right? That sine theta is what we're getting out of that. So with that, then, what we can say is if something is static, so for this static condition, just like my forces, the sum of my torques would be 0. And we're going to define clockwise, so rotating that away as being negative, and rotating counterclockwise going up like that as being positive. But I'm going to tell you this. I'm going to do that because that's what your book does. But it doesn't matter which one you assign the positive or negative to. Your numbers are going to come out the exact same way. The only difference is if you stick to this notation, you never have to define for us whether or not you're rotating clockwise or counterclockwise. If you're changing what you're defining as positive or negative, then you do. That's it. That's all you would need to do. For your mastering homework, though, stick with this to make sure that you keep your signs straight. But so this says that a clockwise rotation, think of it as going down into the negative axes, is negative, and a counterclockwise rotation going this way is going up into the positive axes. There you go. So our sum of torques then, which is kind of nice, is to say that if this thing were to be static, I'd have to have some sort of force going up, right? Because just like our forces that we've been doing all along, if all I had acting on this thing was these two forces going down, then this thing would definitely be rotating. I'd have to have some sort of counter to that. So I would say that the sum of my torques clockwise must equal the sum of my torques counterclockwise. And if I only have one, then that means I have acceleration. I can't be static. So that's something to keep in mind. So now let's see how this applies.